Hey, welcome back. So a while ago I made a video where I built this specialized device which is used to pull extremely stuck seat posts out of bike frames. If you're interested in some of the details, I suggest watching that first, because this is sort of a follow-up video on that one in which we're going to save even more frames. And since there was a ton of comments under that video, I'm also going to respond to some of the most common ones. But most importantly, we're not just going to pull more seat posts, but I'm actually going to deliver on something that quite a few people asked for in the comments, which is to measure how much force it actually takes to remove these things, because I was incredibly curious about that myself. The problem with that is that the type of equipment necessary to measure this kind of thing is pretty expensive, and I can't really justify buying it just to satisfy my curiosity. But thanks to the last video, I was actually approached by a viewer named Tom, who happens to have access to this kind of equipment, so we decided to meet up and actually make this happen. So Tom came over to the shop with a bunch of gadgets, most importantly this thing, which is a load cell. There's all kinds of these cells for measuring different forces, and this one is a tension load cell, which can measure up to 5 tons of pulling force, which should be roughly in the ballpark of what we're dealing with here. So the plan is to hook this up to the existing seat post puller and then hopefully get some valuable data during the extraction process. Before we do this, there's just a few modifications to make for the puller. If you just want to see the measurements, I'm going to put chapters in the video as always, so you can skip ahead to that part, but it's just some minor fixes and mods, so this won't take very long. There's one thing I need to fix, and that is this lower pulling plate. As you could see in the last video, this actually got bent because the forces were so extreme on some of the frames, and it was initially a little bit underbuilt. I did come up with a temporary fix for that, but it also wasn't ideal, so this time I'm just gonna bend it back once again, and then I cut this piece of flat bar here to weld it on as a permanent support in the back. I'm just gonna mill the surface flat here real quick so it can sit flush, and then it can be welded on there. I'm not running full beats here because it would be overkill and it would probably just distort everything, but I'm pretty much certain that this will never bend again with the support on there. The next task is to actually install the load cell in the post puller. The plan is that it's just gonna sit at the end of the main spindle, and luckily this is pretty straightforward, except that the threads don't match, but it's not a big deal. Tom actually brought an adapter, and I decided to just turn down the original spindle on the lathe and then weld that adapter onto it. There would be more elegant solutions for this, but this is just an experiment and we didn't have a ton of time to set this up, so it just needs to work for now. The main spindle can now screw into the load cell, and now we just need one additional modification, and that is this steel plate. What this is going to do is it's going to sit over the load cell and act as a brace that rests against the frame of the post puller, and that's going to isolate the load cell from any torsional forces. When you turn the nut on top, there's not only tension transmitted by the spindle, but due to the high forces and the friction in the threads, the spindle also gets twisted a little bit. Normally this doesn't matter, but the load cell can't have any torsional forces applied to it because it will mess with the measurements and could also damage the cell. So by screwing this plate onto the spindle really tight, we're diverting that force towards the frame before it reaches the load cell. And with that, we're already done with the mods, so everything can be put back together. To give you a bit of foreshadowing here, the screw we used to attach this to the bottom plate here was a bit of a mistake, but you're gonna see what I mean by that later in the video. But for now everything is hooked up, so let's give it a shot. As you can see, I got a whole bunch of new frames that all have stuck seat posts here. Most of these were given to me by friends and people from the local bike scene who saw the last video, but one was also sent in by a viewer who really wanted to save it, and I just want to stress again that the frames that tend to end up here are the absolutely hopeless cases where people have already tried a whole bunch of stuff to remove the posts and failed. This also brings me to one of the most common comments under the last video, which was basically some variant of people saying that you don't need this device because all you gotta do is put a little bit of WD-40 in the seat tube and maybe apply some heat, and then the post basically comes out by itself. And I'm not saying that this doesn't work in a lot of the less severe cases, and it's always the first thing you should try. But every case is different, and at the risk of repeating myself, I can guarantee you that these frames are beyond anything that you can solve with the usual methods. So if you manage to get your post out by spraying some WD-40 or giving it a couple of taps with the hammer, then that's great, and I'm glad you saved your frame, but also it probably just wasn't that stuck to begin with. But apart from the fact that I actually did use oil in the last video, We don't need to theorize about its effectiveness any further because we're actually going to see some pretty interesting data about this today. That being said, I decided to pull the first couple of posts without oil, just to have a bit of a baseline. Unfortunately, the cases are not really comparable, but it might at least give us a rough idea based on whether or not we see a drastic difference in measurements. So let's move on to the first test candidate. This is an older Koga mountain bike frame, and the person who gave me this said they actually found it abandoned on the side of the road and then decided to build a bike from it. But the post had always been stuck, which might be the reason it was abandoned in the first place. As usual, there's already a few signs of previous removal attempts around the seat posts, and ironically the model is called Survivor, so let's see if we can honor that name. As always, I'll first install the custom clamp I made with the appropriate shims for the seat post diameter and then the dummy bottom bracket plugs. So we're gonna have this overview shot in the background here. You can't really see a lot there, and I mostly just shot this to help me synchronize the other footage, but it is helpful to see what's going on with the handle. You can see that at the bottom I have my other camera set up, and that's gonna be filming a close-up of the actual seat post, which we're gonna see on the right here. And then on the bottom left, we're gonna have this screen cap from Tom's laptop, and this is really where the interesting stuff happens, so let's go over that for a second. In the center, we have a diagram that shows us the progression of the tension measured in kilogram force over time, and this is gonna scale up and down dynamically, so since we're not measuring anything currently, what you're seeing here is basically just signal noise within a fairly small range. Then on the top right, we're seeing a little meter for the signal range. So this helps to quickly see where we are within the 0 to 5 ton range of what the load cell is able to measure. So the closer this gets to red, the more likely we'll break something basically. Then below that, we're seeing the current force measured in real time, and possibly the most important info is the max seat post force below that. So the maximum amount of tension we measured at any point for the current frame. I expect some of the engineers and science nerds are going to ask why we're using kilogram force as the unit, since that's outdated and we should be showing the force in Newton. And you're technically right, but the reason is simply that I figured for the average person it's just going to make the numbers a lot more relatable, and it's not like we're writing an academic paper here. So with all the explanation out of the way, let's actually start pulling. As you can see, as soon as I start to turn the handle, the force starts to jump up here. And usually in the beginning, as you apply more force, the clamp just starts to slide up the seat post until it can't slide any further, and that's when we're actually starting to pull the post. So as you can see, we're already up to about 1 ton of force here, so the whole system is well under tension, and we're gonna get the first crack and release of tension in 3, 2, 1. And now comes the part that I think is really interesting and brings me to another comment that came up a lot in some form. There's this really common idea that you just have to get the post moving a little bit initially to quote-unquote break the initial bond. This is often tied to the approach of trying to get the post loose by hitting it with a hammer a few times until it moves, and then it's supposed to have cracked itself loose and be easy to remove. Again, every case is different and this might work sometimes, but from my personal experience with seat posts I removed both before and after I built the post puller, I never saw any evidence of that. Using the load cell should give us a pretty clear answer for whether or not it works this way, because if the breaking the bond theory was true as a general rule, we should be seeing a constant and significant decrease in force now that we got the post moving. But that being said, all of the measurements we took told a very different story, because at the point of the second release we're now actually up to almost 1.4 tons in force. So getting the second crack actually took 300 kilos more than the first one, and this trend continued because the third crack once again required more force than the first. We saw the same trend with all the frames. There was no significant decrease in friction even after having already moved the posts by a few centimeters, and even the fourth crack here still took more force than the first one. At this point the force slowly started to decrease with each crack, but it's a pretty gradual decrease up until the end, so there's never a point where it suddenly just gets easy and stays that way. And even at this point I think it's easy to underestimate just how much friction we still have to overcome here. I don't think you would have been able to move this post with most of the usual methods, even after it was already out by a couple of centimeters, because even now the pulling force we're generating is comparable to hanging both my lathe and my milling machine off the post. In the future, I'd love to actually dive even deeper into this and try which of the household methods, such as twisting the frame in a vise, works at which level of stuckness. But the tricky thing is, it's really difficult to get any kind of repeatability in these experiments, since every case is so different from the last. What I can say is that now that I've worked with a whole bunch of different frames, from fairly mild cases all the way to ridiculously stuck ones, I do think anything that measures more than about a ton to get it moving here is most likely going to be extremely difficult to remove with any of the usual mechanical solutions like vices, hammers, and so on. At this point there's not a whole lot happening anymore, so I'm just going to speed this up. But what we can see is that the seat post was ridiculously long. More of it just kept coming and coming. Now you could theorize that this was the reason why it was so stuck, but so far I can't say I'm seeing a big correlation between seat post length and the level of stuckness. Because as you're going to see in a bit, we also had posts with less than half of this insertion length, and they managed to be twice as stuck. But either way, having a seat post this long, if you don't need it, is pointless at best, so I generally avoid having this much insertion length. So let's move on to the next frame, which is this bomb track. Like all of the frames today, this is also steel, and this is a fairly modern frame, so it's not like this problem only occurs on age-old bikes. This one needed another shim I didn't have, but luckily for the more common seat post sizes you can just buy shims and they're fairly cheap, so I just had to cut this into 2 halves and shorten it a bit. Since this post is black, I'm putting a piece of tape here instead of a marker line so we can see if it moved. We're starting to apply some force now, and you're going to be hearing a bunch of cracks in a second, but those are actually not the seat post moving, it's the clamp sliding to the end of the post as usual. For some reason it made a cracking sound on this one. What this does tell us already though is that this post is way more stuck than the previous ones, because we're already seeing over 2 tons here just pushing the clamp around, and the post hasn't even budged yet. It is going to start moving in a second though. You're going to hear 2 cracks, the first one being the clamp again, and then with the second you can actually see the post starts moving slightly. And just like with the last frame, even after getting some initial movement, the force actually went up. We also started moving the clamp again a little bit, but we're going to get another pretty violent crack from the post in 3, 2, 1... As you can see, we just went up to a whopping 2.6 tons here, so this is now twice as much as we needed for the first frame. And I don't know if you can tell from the video, but at this point it does take considerable force to turn the handle on the post puller. And after having dealt with a few of these, this gives me a pretty good frame of reference for how stuck a post is even without using the load cell. I also think that the maximum of 5 tons we can measure is probably close to the limit of this whole method. I'm pretty sure that as you approach 5 tons, either the seat tube on the bike frame might break, or the seat post, or maybe even the post puller itself. I actually had a friend do some math on how much tension an average chromoly seat tube can take, and that number was also in the ballpark of 3 to 5 tons. That's also why I think making these post pullers even more beefy or using hydraulics, which is also something that popped up in a few comments, is pretty pointless, because the amount of force you can generate with this spindle is not really the limiting factor for this system. It's really more how much tension a seat post or seat tube can take before they snap. And speaking of snapping, we're gonna get the most violent release so far in 3, 2, 1... That one went up to an impressive 2.8 tons, and just like before, there's no sign of the required force dropping off in any way, even now that the post is out by about 2 centimeters. So if you decided to hit this particular post with a hammer from the top to achieve the mythical breaking of the bond, I don't think you'd be doing yourself any favors. We're still in the 2-ton range here, even after countless rotations of the handle and many cracks, but with about 5 centimeters exposed, we started seeing a gradual decrease in force, which usually means the worst is over. As you can see, this one didn't even have a lot of engagement in the seat tube, but the area that was in contact is incredibly corroded, pretty much all around, and there's a really thick layer of aluminum oxide, which is what causes the extreme friction we saw. Next up is this frame, and this one is a bit of a special guest. This is from a local bike store that also sells custom built frames. And if you're affiliated with the fixed gear scene at all, you might have heard of the name Suicycle before. So this is a very nice frame with some pretty fancy tubing, which you can tell just by how crazy light it is for being a steel frame. So I'm hoping the post is not too stuck on this one, because with lightweight tubing like this, I'd be a bit more worried about possibly snapping the seat tube, which tends to be the tube with the thinnest wall thickness. And by the way, the fact that this looks all rusted up is on purpose. This is artificially corroded and then had some kind of clear coat applied, because some people like that look, just in case you thought it was a sign of neglect. As mentioned earlier, since so many people commented on this, I also wanted to try soaking the post in oil to see if the numbers look any different. So I'm spraying a generous amount of WD-40 into the seat tube from the bottom bracket here. I also did another thing that was recommended a lot, which is to apply heat afterwards. This also ties into the idea of breaking the bond that we went over. There's this theory that applying heat and expanding the tubes at different rates somehow causes this supposed bond to break. At this point, after the data we saw, I believe this theory about breaking the bond is mostly just a myth, but I do believe the heat might help the oil to creep into the gaps a bit better. Of course, I also did the same thing from the top, so now let's get some numbers on this one. Again, we're just pushing up the clamp right now, which also caused the shim to take quite a beating because the seat post has kind of an awkward shape. This one was overall relatively easy to remove, and for the first time today the process was more along the lines of what most people expect, where we're seeing a gradual decrease in force right after the first crack. Now I know what you're gonna say, this must be because I put oil in there, but the frustrating part about this experiment is that as much as I'd love to know whether or not that made a difference, there's no way to prove it because we don't have a control. We'd basically have to compare two or more identically stuck seat posts in identical frames to really make a comparison, and I can't think of any way to set that up. So unfortunately, whether or not the oil causes a significant reduction in friction here is still just speculation. But what I can definitely say is that oil and heat doesn't guarantee an easy removal, because the 1.3 tons we saw here is still a huge amount of force, and looking at the post we can definitely see the oil did get in there. So on to the next frame. This one was definitely the most interesting one today for a number of reasons. This is another fixed gear frame that looks like it's seen quite a bit of action until the point where the post got stuck. The post also has more battle scars than any of the ones I've seen before, so someone really tried to get this out. They also drilled a hole down here, most likely to insert some kind of twisting bar. As we can see, that didn't work, and this is an approach I would strongly discourage anyone from trying, because in my experience, 9 times out of 10 this doesn't get the post out, but rather ends with the seat post getting ripped apart, which severely limits your other options. Luckily in this case it's still in one piece, so let's give it a shot. Like with the last frame, I sprayed copious amounts of WD-40 into the seat tube from the bottom as well as on top, and also used a heat gun to hopefully get it to creep in there a little better. So now we can start pulling, and I'm not showing you the measurements right now because we had a bunch of issues with this one before it even got to that point. The first thing that happened was that the head of the seat post actually started to get pulled out of the post. I didn't realize this was happening right away because while you're cranking this thing on top, you can't really see what's going on down there. But when I realized the head was moving, I figured I'm just gonna put a cross bolt in there, which is actually why the clamp has these 2 holes. These are there to be used as a drill guide to put a perfectly centered hole into the post and then insert a bolt for those cases where you can't pull against the head. Only problem with that was, at this point the head had already come out so far that this bolt actually went between the head and the post, which caused it to do absolutely nothing. So I just ended up pulling out the head completely. But that's not a big deal. I just moved the clamp further down, drilled another hole, inserted another bolt using the appropriate hammer, and now we can hopefully move the actual post. At this point there was another little incident. I think the force was at around 2 tons here, and we were waiting for the post to start moving when this happened.
Yo!
I love this short moment of silence when everybody's just wondering what the hell just happened. So let's look at the slow motion. So it's kind of a long story, but what you can see flying away there, and luckily missing any camera lenses and faces in the vicinity, is the bolt that we used to attach the load cell to the pulling plate. This bolt was hollow with an inside thread because it was initially supposed to be used for something else, and I thought I didn't have a solid one, but then it turned out I did. It all takes a bit too long to explain, but the important part is I eventually installed a proper bolt, so now we can continue, which unfortunately leads me to another piece of bad news. The reason I'm not showing you the close-up of the seat post here is that at this point my camera battery died without me noticing, which means I lost the first few minutes of footage for this one. So unfortunately all we got here is the mostly useless overview shot, where I'm blocking half the screen, so we're gonna have to make do with just the data and the sound for a bit here. And what that shows us is that upon the first crack, we broke our previous record of 2.8 tons, with this going up to 2.93 at the second crack. So almost 3 tons to get this moving, and I just want to remind you, this is after I soaked it in oil and applied heat. That means that even after using oil, you could have hung 3 of these welding tables or 1 Range Rover off that seat post, and it still wouldn't have come out. At this point I finally realized my camera wasn't recording and I fixed it, so now we have some footage of the post again. As you can see, it's already out by about 5 or 6 centimeters, and at this point we're still reading peaks of 1.5 tons. I can't say whether or not we would have seen higher forces without penetrating oil, but you can definitely tell it did get in there. Either way, this ended up being another successful extraction, and I'm just gonna speed the rest up again because this kept on going for quite a bit. There was one casualty after this one, and that was the axle that goes into the bottom bracket. Saving this frame required such high forces that the axle got bent quite a bit. In fact, I had to drive it out with the hammer. But that's on me because I just used mild steel for this axle, which is really not up to the task. But I'm just gonna switch this for a solid piece of chromoly in the future, which should be a lot more sturdy. Since we saw the highest load so far with this frame, I also checked whether the bottom bracket shell took any damage, which is a common concern with these devices. But just like with the other frames, the BB cup still threads in absolutely fine, and as mentioned before, I think this C-tube is most likely the weak point for this operation. So we have one last frame for today. This is the one that a viewer actually sent over to me. It's a Fat Chance mountain bike frame from the 90s, and even though it might not look that special at first glance, Fat Chance is kind of a legendary brand, and it has a bit of a cult following, especially now with the whole retro mountain bike trend we're seeing. So this thing is a bit of a collector's item. These things are super sturdy though, so I'm not too worried about damaging anything, so let's try to save it. Unfortunately, before I could get to this one, Tom had to leave and also take his equipment with him, so I don't have any measurements for this one. But it's not a big deal because at this point I have a pretty good feel for where we are roughly on the tension scale just by feeling the amount of resistance in the handle. And luckily this one came out relatively easy. If I had to guess, I'd say this was around a ton or so, which is at the lower end of what we saw today. And before we end this video, here's just a reminder that I also offer plans for this device, which already include some improvements that I made to the design based on the stuff that I broke on mine. And as always, you can find those in the description if you're interested. The stuff that you can see flaking off here is the aluminum oxide that forms when galvanic corrosion occurs between the steel tube and aluminum seat post. And it's important to understand that this isn't rust, or rather it's not only rust. The brown stuff on top is, but this brighter powdery substance is the oxide. It doesn't really stick to stuff like rust, which is why it just kind of falls off here. but it has some serious volume to it, and aluminum oxide is also incredibly hard, which is why it's used as an abrasive for stuff like grinding discs. So it's almost like having this layer of really hard, really fine sand that is easily 1/10 of a millimeter or so in thickness. The stuff keeps growing and expanding between the two tubes, and that creates an insane amount of friction. And when you have enough of that going on, it just isn't really affected by penetrating oils, because those are designed to dissolve rust, which is iron oxide, but this stuff is a completely different chemical, so all the oil really does is to lubricate things a little, and lubricating what is essentially sandpaper can only get you so far. Again, I'm not hating on oil or saying you shouldn't try using it, but at this point I hope it's obvious to anyone who's paying attention that unless you have a very mild case of this problem, oil is only part of the solution, but it can't just magically fix this on its own. But speaking of chemicals, I want to address one last comment that came up a lot, and that was the many suggestions for either using a long saw blade to saw the post into pieces or to dissolve the post in acid. I am aware those solutions exist and they do work, but I consider those kind of a last resort because they're very tedious and time consuming, and in the case of the chemical solution also kind of nasty. But if you just have to save one frame, then of course it's probably still quicker and easier to use those methods rather than building a seat post puller, which obviously isn't a possibility for everybody. I built this thing specifically to use it for many years and save many frames with it, and in that scenario it's definitely the quickest and most effective solution of all the ones I've tried. But if you have a way to do it safely, then using the chemical solution might be your best bet if you've run out of other options. And speaking of options, ParkTool actually made a video recently where they're showing a whole assortment of different approaches for removing stuck posts. If you're dealing with this issue, then I suggest watching that to see some of the different approaches. And it's also good to get a better grasp of the problem overall, because you can also see the limitations of those methods, which don't always work. And that pretty much concludes this video. I hope this was as interesting for you as it was for me. I actually really like doing an experiment for a change, so let me know if you like this type of content, and maybe we can do some more of that in the future. And just one last thing, I actually have not forgotten about the blue GT frame you saw in the last video, since a few people asked about that. I'm still determined to save that one, and I thought I was going to do it in this video, but I had some new ideas for stuff I want to try with that, and maybe even build a specialized tool, so that might actually get its own video. Until then, thanks for watching and see you next time.